After studying in the last class, we have understood how to establish an MQTT connection. Now we will continue learning how to publish and subscribe in MQTT. After we connect to the MQTT server, we can publish messages to any topic. Yes, we don't need to create or register topics on the MQTT server in advance. We can publish messages to a new topic at any time, or stop publishing messages to a topic. This means that we can adjust the business logic of the terminal at any time without any changes to the server. Similarly, we can subscribe to topics of interest on the MQTT server or unsubscribe from a topic at any time. When the server receives a message from the publisher, it retrieves the clients that subscribe to the corresponding topic and forwards the message to these subscribers. However, the server will discard this message if no clients are currently subscribed to that topic. This results from MQTT's feature of not requiring topics to be created in advance. The server cannot know how long a topic will be subscribed by a client, or whether it will be subscribed by more clients, so MQTT servers never cache messages for future subscribers. In MQTT, a topic can be subscribed to by multiple clients simultaneously, and the server will broadcast messages under that topic to all the subscribers. We can also have multiple publishers simultaneously publishing messages to a single topic, and the server will forward them in the order they are received. If there are too many publishers, it may overwhelm the subscribers. In such cases, we can choose to have multiple subscribers consume messages from the topic in a load-balanced manner to reduce the load on each subscriber. This requires shared subscriptions that we will introduce in subsequent courses. By designing topics appropriately, we can freely use the three communication modes: one-to-many, many-to-one, and one-to-one. These modes often coexist. One thing to note is publishing a message from the publisher to the server, and then forwarding it from the server to the subscribers is asynchronous. The publisher does not wait for the server to complete the message forwarding, and the server does not return an acknowledgement to the publisher indicating whether the subscribers received the message. For example, when we send an instruction to turn on the air conditioner remotely using a mobile app, we cannot know whether the air conditioner received the instruction or executed it successfully. Unless we introduce a dedicated topic for the air conditioner to return the execution result, so that we can repeat the instruction if we don't receive a response within a certain period. In MQTT 5.0, we can leverage features such as response topics and correlation data to facilitate elegant request/response interactions. The above are some basic features of the publish-subscribe pattern in MQTT, and understanding them will help us design our applications better. Now let's learn how to publish messages and subscribe to topics in MQTT client libraries or tools. Here's a simple code example, which we usually encounter in the API for publishing messages. It includes several parameters: topic name, QoS, payload, and retain. Topic name indicates the topic to which the message is intended to be sent. QoS represents the desired QoS level for the message, and we can specify the QoS individually for each message. Payload is used to specify the actual content of the message. As MQTT is a binary protocol, the payload can carry data in any format. It can be text data in JSON or XML, encrypted ciphertext, or even binary data like protobuf without base64 encoding. The last field, retain, indicates whether the message is retained. As mentioned earlier, MQTT servers do not cache messages for future subscribers. However, retained messages are an exception. If an MQTT server receives a retained message, it will query for matching subscribers and forward it just like a regular message. However, regardless of whether there are matched subscribers, the retained message will be stored on the MQTT server. Whenever a new client establishes a subscription, all retained messages that match the subscription will be delivered to it. This allows new clients to quickly receive the latest data without waiting for the next message arrival. Another field we need to understand is the packet ID, which uniquely identifies a QoS1 or QoS2 message. Taking QoS1 message as an example, the sender assigns an unused packet ID to the published packet. It considers the message delivered successfully only when it receives a publish ACK packet with the same packet ID from the receiver. Usually, we don't need to manually assign packet ID to application messages, as MQTT client libraries or tools handle this for us. However, in some client library implementations, we may need to use the packet ID to confirm if the message has been successfully delivered. The packet ID also exists in the subscribe and unsubscribe packets, and clients need to use it to confirm if a subscription or unsubscription was successful. We still don't need to set it ourselves, but in some implementations that allow multiple subscription requests to be sent simultaneously, the interface provided by the client library may return the packet ID used for each subscription request, allowing us to correctly match them with the subscription results returned by the server. The only thing we need to care about when subscribing is the subscription list, which can contain one or more subscriptions. Each subscription consists of a topic filter and subscription options. This means that we can create multiple subscriptions through a single subscribe packet or one API call. MQTT provides 4 subscription options: QoS, no local, retain as published, and retain handling. The last 3 options are introduced in MQTT 5.0 and will be covered in future lessons. For now, let's focus on QoS. QoS is the most commonly used subscription option, indicating the maximum QoS level the server can use when sending messages to the subscriber. The client may specify a QoS lower than 2 during subscription because its implementation does not support QoS 1 or 2. And the maximum QoS specified by the client in the subscription is not necessarily accepted by the server. For example, if the server only supports QoS 0, it will set the reason code to 0 in the sub-ACK packet, indicating that the maximum QoS level granted to the client is 0. Likewise, 1 means QoS 1 and 2 means QoS 2. The subscriber can evaluate whether to accept and continue the communication. For this, we have a simple calculation formula. That is, the maximum QoS granted by the server is always the minimum value between the maximum QoS supported by the server and the maximum QoS requested by the client. However, this only limits the maximum QoS that the server can use when forwarding messages, and the original publisher of the message is not subject to this limitation. Therefore, it may happen that the QoS when the message is published is greater than the maximum QoS that the server can use when forwarding. In order to deliver messages to subscribers as much as possible, the server will not ignore these messages. Instead, it will downgrade the QoS of these messages during forwarding. Similarly, we have a simple calculation formula. That is, the QoS of the forwarded message is always the minimum value between the original QoS of the message and the maximum QoS granted by the server. Now you can try performing some publishing and subscribing operations in the client library or tool to validate the content covered in this lesson.